is the partial derivative of f with respect to x. Okay, so there is no, by the way, there is no full derivative for this functions in two variables. There's only the partial with respect to f with respect to x, and the partial with respect to y, which are two different things. There is no full derivative. There is a definition called differentiable, but that doesn't mean that there is a complete derivative that you can ever take. It's always just partial derivatives. Okay. So essentially, what the partial derivative with respect to x is this. Let me try to explain. So you have a point, we'll call that AB. Okay, so you're taking the limit as h goes to 0 of f of x plus h, f of a plus h b minus f of ab. So essentially what happens is the partial with respect to x is you're taking the difference quotient, but coming in along this path here. Okay, this would be, but it's the difference quotient. It's not the limit of the function. It's the limit of the difference quotient. But just coming in along this path, but restricting it to just this path right here. And then Fy would be restricting the difference quotient to this path here, coming in this way, basically. Okay, so there's a partial with respect to x, partial with respect to y. Okay, one other thing that will come up a little bit later is notation. Maybe I talk about it a little bit now. So we have f sub x, but this is also the partial of f with respect to x. It was written this way. Okay, so this is written that way. And then Fy, and is another way to write that one, like that one. Okay, so you'll see both sets of notation. Right now, it's probably more this one right here, f sub x, rather than that. But you know, they're probably going to see both of them about the same number of times. Where it kind of gets tricky is when, if you see something like that, then what this is you take partial in x first, and then second you do the partial in y. So first you do the first one first, and then the second one here. And then what's confusing is that this actually equal to, in the notation, that is that's z. Okay, so you see here's x, y there. X is first, then y. Here, when you do this one, it's x is first and then y. Okay, so that's like the flipped order, and I suppose that can be some confusion. But I don't know. It seems like no one ever gets confused for some reason. Okay, but they're the same. Okay, those are the same. This would be mixed partial. So you can take, so like instead of a second derivative, you can take this one, the mixed one. There's also, you can take two derivatives in the same variable. So with respect to x again, okay, you can do that, or any number of partial derivatives, and with respect to x, y, and then if you have more variables, then it could be z, w, more variables. Okay, so that's how that is. Now, in reality, to calculate these partials, we'll get to that in a little bit later, but I'll mention it right now. To calculate partials, if you have the expression for the function, to calculate the partial with respect to x, you treat all of the variables as if they were constant, except for so like if you're taking the partial of w with respect to x, then you'd treat every variable that's not a w and not an x, you'd treat it as if it was just a constant. Okay. So, but we'll get to that later. Okay. So exercise number 1. Estimate the partial of f with respect to t at negative 1540. Okay, so for this one, right here we have negative 15 and 40, right? So this is the value at the point. It's not the same as the derivative. But you're taking the partial with respect to t. So that means as you're coming in right here, okay? So what we're going to do for this first one is we're gonna do a difference quotient. It will be, okay, as you're going, let's see, these values are negative 10, negative 15, negative 20. So these are smaller values down here, and these are larger values. So we're going to take the larger value, which is negative 21, minus the value out there, minus negative 34 up there. And then down here, we're going to take negative 10. But as long as you get these things straight. Okay, so here, so in other words, this point corresponds to t is negative 10, and f is negative 21. Okay, and then this point, you have t is negative 20, and f is negative 34. Okay, so as long as like this gets put in the same slot, okay, and this gets put in the same slot, then you're fine. Okay, so these could be reversed. We could have negative 34 minus a negative 21 over negative 21 minus a negative 10. That would also work. Okay, so here you're going to get, the numerator is what, 13, and the denominator is 10. So you get 1.3. What the? Okay, 1.3 is what you get. Okay, so we go ahead and put 1.3 in there and see if that works. And in the partial with respect to v, that's the next question right there. So there's this one right here. And for this one, you're going to take a look at, you're going to go this way. Okay. So for that one, let's see, let's choose this point first. So that's a negative 29. And there's a 50 there, because that's at 50. And then this is at 30, and that's a negative 26. That's going to be negative 3 over 20, which is, what's negative 3 over 20? Negative 1.5? Wait, no, that can't be. Negative 0.15? I don't know, negative 0.15? Yeah, so this is 1.3 and this is negative 0.15. Okay, what are the practical interpretations of these? When the actual temperature is negative 15 and the wind speed is 40, which is this point here, the apparent temperature would
that be rises?
Yeah, rises. By, okay, so it'd be rises by 1.3 Celsius. And then the second one would be decreases by 0.15. Okay, and then the next part, in general, what can you say about the signs for a fixed wind speed? The values of the wind chill factor W increase as the temperature increases. So it's positive, and then the other one's decreases and negative. Wait, the value of W as V. Wait, as V and what? As V increases. Oops, that's increases also. Oops. That's negative. Okay, now this last part, what appears to be the value of the following limit? The limit as V goes to infinity of dV, dW, dV. Okay, so as you're moving out here, your wind speed is getting more and more, right? And so here, let's follow one of these lines. This went down by 3. This went down by only 1, and then this one went by 1. That one 1. Okay, this went down by 2, and then another 1, and then another 1, and then another 1, and then just went down by some, but probably by less. So the amount that it's going down is decreasing, right? As we're moving along the table here. So that means that if that's the case, then if you're taking this to infinity, that would be pretty violent there, with winds that are greater and greater speed, then it's going to be 0 eventually. The change is going to be 0, going to 0. Okay, let's look at number 2. Okay, so here it says determine the signs of the partial derivatives for the function f whose graph is shown. Okay, so you're looking at the partial of f with respect to x. Okay, so here, see right here, with respect to x, that means you're going in along here, because this is the x-axis. So this is kind of where you're at. So now as you move along this, as you move in the positive x direction, is your graph going, are you going up on the graph or down on the graph, or staying the same level as you're moving this direction?
Go up.
You're going up, okay? So the answer is going to be positive. Okay, now the partial with respect to y. Okay, this is the positive y direction. So you're looking at it this way. So as you're going along the path right here, are you going at that point, or is it going down or going up?
Down.
Down. So this is going to be negative. Okay. So positive, negative. Okay, now number 3. Okay, determine the signs. Okay, so here's the mixed partials. Okay, so this means you're taking, and they got 2 different points. Okay, so here you're taking the partial with respect to x, right? And then the partial with respect to y. Okay, at this point. So now, this is a bit more tricky. or maybe a lot more tricky, who knows? Okay, so let's take a look at this first. So the partial, let's look at the, think about the partial with respect to x, right? Okay, so here, this is the positive x direction, right? And this is increasing, right? So fx is positive. We already established that because this is the same graph, right? Okay, now, if you're going to take the partial of that, so that's positive, right? Now, if we look at if we look at the y direction, that's this right here. And so now the idea is as you come in, as you're going this way in the positive y direction, what's happening to these partials with respect to x? Okay, are they getting, so if you go here to there to there to there, are these slopes getting, the slope of these blue lines at these points right here, are they getting bigger or are they getting smaller? Are those slopes getting bigger or smaller?
Looks like they're getting bigger.
Yeah, they're getting bigger because this is pretty flat and this is more pronounced and then this is more that. So that means that this is going to be positive, right? Okay, the slopes are getting larger. What? So that means positive. Okay, now let's take a look at the same thing at this other point over here. And again, this is the positive x-axis, right? This is the positive x direction from that point. So what does the slope look like right there? Ooh, this is kind of hard to see. Dang. What's the slope look like there? I can't really tell. It looks like it's going down, right?
Yeah.
Okay,
It's
and then
flatter, I would say.
It's what?
I think it's getting flatter, so it'd be negative.
Yeah. So this is going down faster, and it's going down at a slower rate, and then it's already down right over here, so it's negative. Okay. Yeah. Plus, you usually put one of each, right? If the first answer is positive, then the next answer is probably going to be negative, right?
Oh, that's true.
That's true. There's like some theorem there, maybe along those lines, maybe. Okay. So let's see, number 4. I mentioned before how to calculate partial derivatives. And it's basically just like a regular derivative, except, okay, here's your f right there. And here's an x, right? But this is a y, which is a different variable. So this is different than your f and your x. So you just treat that as a constant. Okay, and then 25 is a constant, so it gets treated as a constant all the time. Used to it. Okay, and then, so this is, the derivative of this is going to be negative 25. Wait, no, what am I doing? Whoa. Okay, that's negative 10x, right? And then this is 0. Just treat that as a constant. So that's just 0 when you're taking the partial. And then partial with respect at negative 5, negative 2, or 5, negative 2. That means you plug a 5 in for x and a negative 2 for y, but there's no y. So the answer is negative 50. Okay, and then what is f, the partial of f with respect to y? So here you treat that as a constant. So that's just 0. And then you get negative 2y. Right? So plug a 5 in for x and a negative 2 for y. And that's going to be positive 4. Okay, so 4 is the answer to that part. Ooh, 4 is the answer to number 4. No, it's one of the parts of 4. Okay, so let's see. Number 5, find the first partial derivatives of this guy right here. So they want fx and they want ft. Okay, so anybody want to take a crack at this? So here, you just treat the t as if it's a constant.
And wouldn't that just be 0?
Yeah, that part's going to be 0. And then by the product rule, though, you're going to have, or you don't have to do the product rule because it's just that you just think that's just a constant out there. What's the derivative of
negative e to the negative x?
Yeah, but you'll have the t to the 4th there.
Right.
Okay, so that would be like if you have like 17 e to the negative x, it would be negative 17 e to the negative x. Okay, and then what about this one? That's the partial with respect to t.
It'd be 4t to the 3rd e to the negative x.
Yep. Okay, so I'll put those answers in and see if Webassign is taking it. Okay, good. Number 6, we're supposed to find the first partial derivatives of this guy. W equals the natural log of x plus y. Let's see, so now here, this is where the other notation comes into play. Because W is kind of on the same level as X, Y, and Z, all right? X, Y, Z, W, maybe is the next one. So the partial, so WX, we write that as partial of W with respect to X. And then you also have partial of W with respect to Y and partial of W with respect to Z. So we'll have to just find those 3. Those are going to be, and then 3 answers that we're going to put in. Okay, so what's the partial with respect to x? So here you have the x right there, and these guys just get treated as constants. So I'll start this one off. So it's 1 over whatever is inside the logarithm times the derivative of the what's inside. And the derivative of this, or the partial of all of this with respect to x is just going to be 1. Because the partial of x with this derivative of x with respect to x is 1, and then these are just zeros. Okay, and then this one, the partial with respect to y is going to be 5. And then this is going to be 7 over here. Like that. Okay, so let's see if Webassign agrees. Yeah, it looks good. Okay, number 7. use implicit differentiation to find the partial of z with respect to x and the partial of z with respect to y. Okay, so here, instead of being z equals some stuff, you have e to the 5z equals that stuff. Okay, so what you're going to do is take the partials with respect to x, first of all. Everything that's not a z or an x, it's not a z or an x, everything that's not that one or that one, you treat that as a constant. This one you treat as a function. So the derivative of that would be e to the 5z times the derivative of this, which is 5, times the partial of z with respect to x. And then over here, you take the partial of this with respect to x. What are you going to get? Now, the y and the z are like constants. So you're just going to get yz. Okay, because the derivative of that's 1, and then those are just carry those over like constants. And so you're going to get, if we divide by 5 e to the 5z, you get that. But then it's probably a good idea to cancel the 5s. But then also, e to the 5z, you know, is this xyz. Whoa. This is just going to be 1 over x. 1 over x. That's interesting. Whoa. Wait a minute. What am I doing? Why did I put a 5 there? Where did that 5 come from? Oh dang, I don't know where I went wrong here. But Webassign is not liking my answer. Anybody see it? Anything? Oh, I know. There's a z there also. Ah. Okay. So this should be plus xy partial of z with respect to x. Okay. Okay, so I can erase all this. Boo. Okay. So that means we're going to take this to the left side. So you have 5 partial of z with respect to. We'll take this to the left side and factor out a we'll take this to the left side and we'll factor out a partial of z with respect to x. And that leaves with this 5 e to the 5z minus xy equals yz. Okay, then you take this to the other side. 5, and then e to the 5z is just going to be this. So that's xyz minus xy. And the y's are going to all cancel out, right? So you get z over 5xz minus x. Okay, let's try that one. See if they accept that. Okay, good. They accepted that. So that means that are the same because x and y are pretty much the same or symmetric with each other. That means that the partial of z with respect to y, it should be z over 5 yz minus y. So just replace all the x's with y's. Should work out. Okay. So let's take a look at number 8. Find all second partial derivatives. And so here we have TRR. Okay, so first of all, the partial with respect to r of t. Okay, now there's no t's over here. They're just r and theta. So you're taking the partial of this with respect to r, and you're going to get negative 5, e to the negative 5r. And then the cosine theta is just like a whole constant. So it just goes like that. And then if you take another derivative, you're going to get another negative 5 coming down. So that's 25 e to the negative 5r cosine theta. Okay, and then if you take t theta, then this is all a constant. So you're just taking the derivative with respect to cosine, which is negative sine, right? So that's going to be negative e to the negative 5r sine theta, and then the second partial there is going to be e to the negative e to the negative 5r, and then this derivative of cosine is just cosine. Like that. Now, you also have the mixed partials, TR theta. That would be where you take this right here, you take the partial with respect to theta. So that's the negative sine, so that's going to be 5 e to the negative 5r sine theta. And if you do theta r, then that's taking the derivative with respect to r now. So you have a negative 5 coming down. So that's going to be 5 e to the negative 5r sine theta. Okay, notice that these are the same. Okay, and that's typically going to be the case if all functions are continuous, then there's a theorem that says that these are going to be the same. Okay, so TR theta equals T theta R. So it doesn't matter the order usually of what you take these guys in, that you're going to get the same answer either way. Okay, I'm just putting these things in. And I copy and paste that one. Okay, so that brings us to number 9. We're technically out of time. Yeah, we should probably stop about right here because we're out of time. It's 10:52. And we're supposed to end at 10:50. So we're out of time. But this is the last question that we're going to go over for this section. We'll do a little bit, we'll do this tomorrow.